Hello, in this video I'd like to talk about the Myhill-Nerode theorem. So suppose that we have two copies of the same deterministic finite state automaton with this particular transition graph. And suppose I start typing two different words into the two different automata. Let's say in the first automaton I start typing the letters AA, and into the second automaton I start typing the letters BB. Now, both of these sequences of characters are going to take our finite state automaton into state 1. It's important to remember that the state that a finite state automaton is in is all of the information that it has kept about the past. It does not remember the entire sequence of characters that got it to the state that it's currently in. It just remembers what state it is currently in. And so, these two automata are in the same state. They have the same memory. They remember the same information about the past. Specifically, all that they remember is that the sequence of characters that they've seen so far is one possible sequence of characters that will get them from the start state to state 1. Because these are the same finite state automaton and they're in the same state, no matter what I type in next into the first automaton, as long as I type the same thing into the second automaton, we're going to wind up in the same states, and in particular, that means that the indicator light is going to either be both on or both off, depending on whether the state I wind up in is an accept state or not. Contrapositively, if I type in two sequences of characters, and either the indicator lights are already in a different state, or there's some sequence of characters that I can type into both of these automata to make one of the indicator lights go on, but not the other, then we know that these two words, these two sequences of characters, do not put our finite state automaton into the same state. However, this isn't exact. It could be the case that there are two words that I could type into my two automata that would put me into different states. However, no matter what sequence of characters I type into both of these copies of the automaton, the indicator lights are either going to be both on or both off. In this case, our finite state automaton has kept track of information that it didn't need, and we can take these two states and we can actually merge them together into one state. Simply take all of the arrows that are pointing into one of these two states and move them so that they're pointing to the other state, and then we can eliminate the state that doesn't have any arrows pointing to it because it's unreachable. We now have an equivalent automaton with one less state, and one less state means we're using slightly less memory. And this procedure allows us to construct a canonical minimal form of our automaton. The key thing to note here is that the order that we merge equivalent states together in doesn't matter, because if we merge two states together, the result is going to be equivalent to anything that was equivalent to the original two states. And so we could merge two states and then merge a third state in, or we could merge two states and then merge a third state in, and it doesn't matter the order that we decide to merge these states in, they're still going to be equivalent, they're still going to be mergeable. And so we can merge all equivalent states together into one state, and once we've merged all of our equivalent states together, we can't do any more merging, and so this really is the canonical minimization of our original automaton. But the clever thing here is that this minimization process doesn't actually depend on the states of the automaton. Remember that we were just looking at whether the indicator light was on or off. We were only concerned about the language, the set of words that would make the indicator light go on. As such, we'll be interested in looking at the ways of taking the start of a word and continuing it to get something that's in our language. So first we need to fix our language L, and this can be any language. It doesn't have to be a regular language, but it might help to think of this as a regular language. So here, given a word, we're going to define its future to be the set of words that we could concatenate onto the end of this word to wind up in this particular language. And this is exactly the same thing that we were looking at when we were looking at states. Note that in the case that L is a regular language, this is actually also going to be, so the future is a language, right? It's a set of words. And so if L is a regular language, this future is actually also going to be a regular language. And the deterministic finite state automaton that recognizes it is going to be the same as the automaton for L, just with a different start state, specifically the state that you wind up getting into after you read W for the original automaton. We're then interested in talking about when two words have the same future. So we'll say that two words, W0 and W1, are, this is a tilde sub L, and we call this Myhill-Nerode equivalence. We say that W0 is Myhill-Nerode equivalent to W1 if they have the same futures. In other words, two words are Myhill-Nerode equivalent if for any word V, both words with a V tacked onto the end are either in L or not in L. This here is a binary relation similar to a binary operation, but instead of outputting another word, it's just going to output true or false. And in particular, this relation here is going to be what we call an equivalence relation. Equivalence relations are required to satisfy these properties. What this means is that we actually have two bits of structure on the set of words. We have both the monoid structure of concatenation, and we also have this Myhill-Nerode equivalence. And very often when you have structures that have two aspects to them, you're going to want those aspects to play nicely with each other. For instance, when we have structures that have addition and multiplication, we're often going to want distributivity. And then additionally, if we have a linear ordering, we can require that linear ordering to behave nicely with respect to addition and multiplication, giving us all in all the definition of what it means to be an ordered ring. Similarly, Myhill-Nerode equivalence plays nicely with monoid concatenation in this way. It's important to note that if two words are Myhill-Nerode equivalent, then either they're both in the language or not in the language, because we can just look at this property here and consider the case where V is the empty word. Equivalence relations describe a way of partitioning up a particular set. In this case, we have an equivalence relation on the set of words, and so what we have is a way of partitioning up the set of words into lots of different pieces, such that anything in one piece is going to be Myhill-Nerode equivalent to anything else in that piece, and is not going to be Myhill-Nerode equivalent to anything in another piece. We call the pieces of this partition equivalence classes, and the Myhill-Nerode theorem says L is a regular language if and only if Myhill-Nerode equivalence over the language L has finitely many equivalence classes. So this is a very abstract way of categorizing the regular languages. Let's try to look at this from a slightly more concrete perspective. Let L be any language, and again, you can think of L as being a regular language, or some sort of non-regular but computable language, but L can be any language. There's tons of sets of words that are far beyond the capacity for computers to deal with, that are uncomputable, that maybe solve the halting problem, or something like that. Nonetheless, we can still find an infinite state automaton that recognizes our language L. An infinite state automaton is just a finite state automaton, but we don't require there to be finitely many states. In particular, the transition graph for this automaton is going to look something like this, and each state then represents a particular word. That is, that there is exactly one word that will get us to each state. We then decide whether these states should be accept or reject based on whether the corresponding word is in the language or not. So this gives us an infinite state automaton that recognizes our language, and then we go through a minimization process. We merge together all states that have the same futures. In other words, we merge together the states whose corresponding words are Myhill-Nerode equivalent to each other. As such, if there are only finitely many Myhill-Nerode equivalence classes, our merged automaton, our minimized automaton, is going to have finitely many states. And so our language is going to be regular because here we have a finite state automaton that recognizes it. On the other hand, if we weren't able to merge things together enough to get only finitely many states, then what we're left with is a minimal automaton with infinitely many states. This means that there is no finite state automaton recognizing this particular language, and in that case, our language is not regular. So that's how the proof of the Myhill-Nerode theorem works. Let's take a look at this process for a few concrete languages. Let's go back to our language, which consists of the set of words with an odd number of A's and no C's in them. So we're going to add C back into our alphabet, but we're still not going to want to have any words that have C's in them. We can then make a chart to try to discover the Myhill-Nerode equivalence classes for this particular language. Let's start with the empty word. What is the future for the empty word? Well, what sorts of things can we add on to the empty word to get a word in this language? Well, specifically any word in this language. So that's going to be the future for the empty word. What about the word A? Does the word A have this as a future? No, we can't take a word with an odd number of A's and no C's and tack that on to the end of an A and expect to get a word with an odd number of A's and no C's. That isn't going to work. So in a different Myhill-Nerode equivalence class, we're going to have the word A. And the future for that word, well, what sorts of things can we tack on to the end of the word A to get a word with an odd number of A's and no C's? Well, it's just going to be words with an even number of A's and no C's. Let's take a look at another word. What about the word B? Well, B has the same future as the empty word. B, if we tack on a word with an odd number of A's and no C's, we're going to get a word in this language here. So B is going to be Myhill-Nerode equivalent to the empty word, and it's going to fall into this first equivalence class. And finally, what about the word C? Well, C, there's no way of tacking something onto the end of the word C to get something in this language. So the set of futures for C is the empty set. We can then look at the words of length 2 and try to figure out which ones of those fall into these various equivalence classes. For instance, AB is going to fall into this equivalence class because if we tack on a word with an even number of A's and no C's, we're going to get something in our language. On the other hand, AA is going to be in this equivalence class, and so on and so forth. In fact, any word with an even number of A's and no C's is going to fall into this first equivalence class. It's going to be something with exactly this as its future. And words with an odd number of A's and no C's are going to fall into the second equivalence class. And finally, any word with C is not going to have a future, and so it's going to fall into this third equivalence class. These three equivalence classes define the three states of our minimal automaton recognizing this language. Let's call this state 0, let's call this state 1, and let's call this state 2. We can then construct a transition diagram for these states by looking at what happens if we take a word in each of these equivalence classes and tack a particular letter onto the end of it. So suppose that we have something in the equivalence class 0, and we tack an A onto the end. Well, if we take one of these words and tack an A onto the end, we're going to get one of these words. And so reading in an A is going to take us from state 0 to state 1, from the state of having read one of these words to the state of having read one of these words. On the other hand, if we take one of these words and tack a B onto the end, we're going to get another one of these words. And so if we're in state 0 and we read a B, we're going to wind up back in state 0. If we're in state 1 and we read an A, we're going to wind up with a word in this collection here. And if we're in state 1 and we tack a B onto the end, we read a B, we're going to wind up back in state 1. And if we take any of these words and tack a C onto the end, we're going to wind up in this state here. And if we take any of these words and tack either an A, a B, or a C onto the end, we're going to wind up here. So we were able to construct, and this should look familiar, this is the minimal finite state automaton recognizing this particular language. As such, just by looking at the Myhill-Nerode equivalence classes, we were able to determine not only that this language was regular, but also a finite state automaton and the minimal finite state automaton that recognizes that language. Let's take a look at another language, this being a language that we don't know whether or not it's regular yet. Let's look at the set of all words of the form n a's followed by n b's for the same n. So this is going to contain things like the empty word AB, AABB, AAABBB, and so on and so forth. It's common to use this exponential notation in monoids, even if it's not quite as nice as regular exponentiation of real numbers. So let's make a chart of the Myhill-Nerode equivalence classes. Let's start with the empty word. What is the future for the empty word? Well, it's just going to be this entire language here. Words of the form a to the n, b to the n for some n. What if we have the word a? Well, the futures for the word a, we could either have just b by itself, or we could have a, b, b, words of the form a to the n minus 1, b to the n, where n minus 1 has to be at least 0, where of course we interpret a to the 0th as being the empty word. On the other hand, if we have the word aa, the future for that, it's not going to be either of these. It's going to be a to the n minus 2, b to the n for various values of n. And so on and so forth. If we have the word a to the k, the future for that is going to be words of the form a to the n minus k, b to the n. So each of these words, each of the words of the form a to the k is going to have a different future, a different set of words that we can tack on to the end in order to get a word in our language. As such, we have infinitely many states. And we haven't even looked at all of the words yet. We've just looked at the words that start with A. What about the words that look like A to the K, B to the J? Well, each of those is going to have a different future from this, right? For these words, we can only tack on words that consist of some number of B's. And so none of these options exclude having more than one A at the beginning. So these words are going to have their entirely different set of futures. And so what we've done is we've proved that there are infinitely many Myhill-Nerode equivalence classes for this particular language. In other words, this is not a regular language. There is no finite state automaton that recognizes this language. Nonetheless, we can still use this to construct a minimal infinite state automaton recognizing this particular language. So we can have one state representing that we've just read the empty word, and then we'll have another state. If we're in that state and we read in an A, we're going to wind up in this state. If we're in this state and we read in an A, we're going to wind up in this state, and so on and so forth. But we're going to have an infinite sequence of states, and then we also need states corresponding to things of this form, and we'll also need a big failure state for words that have no future. There are plenty of words that could not possibly be the start of a word in this language. For instance, something like BA couldn't possibly be the start of a word here. So we need some sort of failure state to indicate that we're in a Myhill-Nerode equivalence class for words that have no future. So I'll let you, if you want, try to finish this infinite state automaton, but as far as we're concerned, because this series of videos is just about regular languages, as soon as we've proved that this language is not regular, we're no longer interested in it. So thanks for watching, and I hope to see you in a future video.